Hi, my name's Bob Grunier, and I'm a volunteer with the Martin Fleischmann Memorial Project. So welcome this Friday, 10th November 2023, for THOR Magnetic Anomalies. This is a bonus presentation for you keen people out there. Hi, hi NG, hi Artifact, and hi Corky Goss. It's a pleasure to have you in the room. So, earlier this week, I did a 25-hour turnaround to the UK and back, and the reason was I had an opportunity to have a look at the first small and first large thunderstorm generator of Malcolm Bendall, and what I wanted to do was to get some understanding of if there was any anomalies in there, have a think about that when I got some footage, and also to get some really close-up eyes on the inside sphere of the thunderstorm generator, the one that was on a Perkins for about 8 years. Apparently it ran for hundreds of hours, not thousands of hours during that period, and there were some interesting things on there, and I was very concerned that if there wasn't a very quick capture of its status, that it could deteriorate. It was wrapped up. However, you know, it's more exposed than it was when it was kind of like covered over with the other steel ball, and, you know, dust can get in there and stuff. So whilst I was not so interested potentially in the actual sample that I could potentially get if I wasn't going to be able to take a section of the device, I wanted to capture as early as possible the potential for spatial arrangements of materials, because that is really where this science is playing out, not in the various things which people can obviously say are contamination. Unfortunately, this system likes to create stuff that is in the Earth's crust preferentially, and I've argued since 2019 that the answer to what this system does is the Earth's crust, and so that's not surprising. And so I think it was very productive, and I'm going to talk through a couple of the things that were observed, and I hope I will be able to give a sufficient explanation for why they have occurred and what that means for future thunderstorm generator construction, and also what possibly may be going on. So I was very, very encouraged actually by the SEM session I did with a sample that I took off the other large thunderstorm generator a while back, and this had this potential sacred geometry structure with some aluminium on each of the centers of both cores. And as we know, silicon is the second most abundant element in the Earth's crust, and aluminium is the third. Obviously, oxygen is the most abundant. So to find both silicon and oxygen and aluminium in there, like I say, it could be contamination, but it's when you see it in these structures that it becomes interesting. So what did we find? Well, how is everyone? Can they hear me? It says excellent connection, but it does seem to be buffering on the screen here. So can you see me? I think what I'm going to have to do is come in and out of the window here just to see if it's actually working here. Sometimes that is what needs to be done. Okay, I can't see myself on the stream going out, so it might just be that I need to. There we go. I've refreshed the window here. Okay, yes, that's the same for me. Wait. So hi Lucas, hi Nathan Ford, hi It's great to have you here in the house. Okay, so we're going to start by looking at the first video here, where we went over the remaining parts of the thunderstorm generator, the small one, the original one, and I'll just zip through that video. I actually need to find it, so if you bear with me, because there are some things which are interesting, but what are they actually telling us? That's the question. Right. Okay, so where would that be? Actually, as a primer, I'm just going to talk about magnets. And the two magnets that I've seen Malcolm Bendall using in demonstrating magnetic anomalies. It's now buffering again. Is this a problem for other people? Okay. All right. Let me just see. Let me just see. It might be because the pub downstairs might be grabbing some of the data here. It's all good. Okay, so I've just got an issue on my end. Right. Okay. So hopefully you're going to get this. We will know soon enough. He's used sphere magnets and also disc magnets. This is a disc magnet with a hole in it. I haven't seen him use one like this, but in both cases, the magnets have a radius, okay? And one might imagine that the magnetic field line connection between a radius or a spherical, sorry, a disc or a spherical magnet, when you are on a flat surface, you've got a certain amount of reconnection or connection to the ferrite material, or sorry, the ferromagnetic material. When it's on a convex surface, you've got less connection. And if you are conversely in a crack like that, yeah, or a crack like that, you've obviously got more magnetic field lines connecting to the surface. Okay, so when we are on a, and then also if you have thin metal, so if you take my finger being thin, that will have a certain amount of attraction to it. And if my thumb was another piece of iron, it would have more attraction to it because it's a thicker piece of ferromagnetic material that can be magnetized. Okay, and so yeah, so one can say if we are on a flat surface, that will be, well, basically that the highest strength connection given the same material would be when you have a crack, okay, that's got thick metal underneath it. Okay, the next one would be thick metal on a flat surface, and then the next one would be thick metal on a convex surface. The weaker the thinner the material, the weaker the connection will be. Okay, so when you are looking at the videos and you're seeing things connecting more strongly in certain places than others, you have to bear those things in mind. Then there's also the magnetic susceptibility and the actual properties of the metal. So like some ferromagnetic materials are slightly ferromagnetic because they have less domains that can align, and some are more. And so these are the kind of considerations you have to think about. Now, let me find the video, the first of the videos there. I want it off my server so we don't have adverts getting in the way. So let's have a look at this. I will find it, honest. Or not, may be the case. Failing that, I will actually have to go to YouTube. So has anyone got any inspiration or comments on what they've seen with regard to what I've shared yesterday and today from what was captured on the 8th? Oh, this is not very good, is it? Honestly. Oh, where's it gone? Right, I'm going to have to go to the YouTube. Sometimes it's good to have a backup, and in this case, that's what it is. Right, so we'll have to take it off YouTube then. See if this will work in a window. All right. So here's our friend Malcolm, and he's got his thunderstorm generator there. I'll put this to 4K. Or maybe not. Maybe that was a bad idea. So, when you are looking at this device here, can you see what I have on the screen? Sorry, there's a lot of streaming going on at the moment, so I can't tell whether you're actually seeing what's going on. Okay, good, because I can't actually tell whether I'm actually streaming right now, which is a little bit tedious. Okay, so Malcolm talks about the fact that this particular device was reused, and there is an area here where the swirl guide for the input from the engine was on the wrong side and it didn't work, and they re-welded that up and seamed it up and placed it on the other side, and it did work. And as we go through here, Johanna James, who was there, shows me these cracks in here. And first off, someone correctly identified that when you weld to stainless steel, sometimes you can get the chromium coming out and it forms like chromium carbonate or something, and this ends up by being a point of failure in welds, or when you're trying to do it potentially in a less than ideal way. So there could have been weak points because of this. But the key point of discussion here in this video was this so-called collapsed area, this so-called imploded area. And certainly when I ran a magnet over it, the magnet was very keen. As you can see, Johanna's just placed the magnet on there, and it seems very keen to grab to this tube here. And I got the impression that this tube was soft iron, whereas this was more likely steel, but that definitely on the point of deformation, it was not magnetic because we put Magnaview film on there, but it did seem to have some ferromagnetic nature or paramagnetic nature, such that the magnet would attach itself to this bit also, not just this. Okay? So it really was very attracted to that. Then when it comes to the steel ball itself, it really did seem to be more attracted to the weld point, even though that's convex. And so that would be, as per my little primer earlier, the place you would less expect it to bind to. But I argued that, again, you know, there could be something going on with the thermal aspects of the welding process, and maybe that's what's going on. But I have to agree, there was a certain amount of ferromagnetic nature to the unsort of area, the non-welded area, this big curved section here, and you can see Johanna putting it on there. But whilst it did feel like it wanted to be there, it felt a lot more attracted to the more ferromagnetic areas around the welds. Okay, and then particularly in this concave section of the steel ball joining the steel tube, there was this strong binding there where the weld was too. So those things being said, and the other thing is, I noticed that this appeared to be ferromagnetic material, and that is very important. So with that being said, I think this is probably the key little takeaway here, or rather image, and I'm going to probably just grab that and we'll dump that into a slide so that we've got it for later. Well, I'll just leave it there in the oh no, it's not going to keep it now. I should have done that. I will. Right. Okay. Anyway, so what I would like you to do a quick search for right now, and maybe I can post it in the YouTube here. I might just post this link. You can read it, but I'm going to summarize this, or rather the key parts of it. It's quite a short little piece of text, so let me just copy this into the chat so you can go and look at it in real time. He says, is it going to respond for me? Not having a lot of luck today. Okay, so I'm going to dump this into the chat here. So go and have a look at that Scientific American article. It is the key article that I'm going to discuss in the next couple of minutes. And we will throw it up on a slide here. Okay. So, why don't magnets work on some stainless steels? This is in Scientific American, and it's by Thomas Devine, a materials science and engineering professor at the University of California, Berkeley, and he provides this answer. Stainless steels are iron-based alloys primarily known for their generally excellent corrosion resistance, and you heard Malcolm referring to that's the reason why he uses stainless steel, which is largely due to the steel's chromium concentration. I've just talked about how when you're welding, sometimes that can come out and it can produce this brittle area. There are several different types of stainless steels. The two main types are austenitic and ferritic, each of which exhibits different atomic arrangement. Due to this difference, ferritic stainless steels are generally magnetic, while austenitic stainless steels usually are not. A ferritic stainless steel owes its magnetism to two factors: its high concentration of iron and its fundamental structure. Right. The metallic atoms in an austenitic stainless steel are arranged on a face-centered cubic FCC lattice. The unit cell of an FCC crystal lattice consists of a cube with an atom at each of the cube's 8 corners and an atom at the center of each of the 6 faces. In a ferritic stainless steel, however, the metallic atoms are located on a body-centered BCC lattice. The unit cell of a BCC crystal is a cube with one atom at each of the 8 corners and a single atom at the geometric center of the cube. Alloying the stainless steel with elements such as nickel, manganese, carbon, and nitrogen increases the likelihood that the alloy will possess the face-centered cubic crystal structure at room temperature. Face-centered crystal, that is austenitic, okay? So, chromium, molybdenum, and silicon make it more likely that the alloy will exhibit a body-centered cubic crystal structure at room temperature. Right. The most popular stainless steel is type 304, and I know that Malcolm has discussed using this. The other typical one you might consider is 316. I think that has more nickel in it. Anyway, which contains approximately 18% chromium and 8% nickel. At room temperature, the thermodynamically stable crystal structure of 304 stainless steel is a body-centered cubic. Nevertheless, the alloy's nickel concentration, as well as the small amounts of manganese, about 1%, carbon, less than 0.08%, and nitrogen, about 0.06%, maintains an FCC, face-centered cubic structure, and therefore the alloy is non-magnetic. So it would ordinarily be ferromagnetic, but because of these additional elements in here, normally the alloy is non-magnetic at room temperature. If the alloy is mechanically deformed, i.e. bent at room temperature, it will partially transform to the ferritic phase and will be partly magnetic or ferromagnetic, as it is more precisely termed. Right. So if you have this stainless steel and you deform it, you may get a situation where it becomes partly ferromagnetic. Okay? So is that what we saw? Potentially, and I'll go into why in a minute. Popular ferritic steels are iron chromium binary alloys with 13 to 18% chromium. These alloys are ferromagnetic at room temperature. Like all ferromagnetic alloys, when heated to a high enough temperature, their Curie temperature, their ferritic stainless steels lose their ferromagnetism and become paramagnetic. That is to say, they do not retain their own magnetic field, but continue to be attracted to external ones. A piece of ferritic stainless steel is typically unmagnetized. When subjected, this is very important for the second part of what I'm going to say. When subjected to a magnetic field, however, it will become magnetized. Oh, you can't see it, can you? Why can't you see that? Can you see it? Okay. It will become magnetized, and when this applied magnetic field is removed, the steel remains magnetized to some degree. Right, so if you have something that is ferritic, either it starts ferritic or it becomes, ferromagnetic, then it will be able to be magnetized. Okay? And so I've said to the people replicating this technology that they need to consider doing their tests with a magnetometer first before they run an experiment, and before they apply a magnet to the device. There is a way to like reset it, but it's going to be problematic for the materials potentially. Okay, so when subjected to a magnetic field, however, it will become magnetized, and when it is this applied magnetic field is removed, the steel remains magnetized to some degree. This behavior is a consequence of the steel's microstructure. Specifically, in its natural state, ferritic steels consist of small regions called magnetic domains, which are fully magnetized. But in general, the direction of magnetization is different in each domain. As a result, the sum total of all domains gives a piece a zero magnetic moment. An external magnetic field orients these magnetic domains. Depending on the steel and the applied field, the orientation is achieved by a combination of selective growth or shrinking of particular domains and the rotation of magnetization within the domains. If the applied field is sufficiently strong, the steel will retain a significant fraction of its magnetization as long as the steel has an adequate number of imperfections that keep the domains from rotating and growing or shrinking. Fundamentally, the reasons why ferritic steels are ferromagnetic while austenitic steels, stainless steels, are not, are quantum mechanical in nature. Suffice it to say, a ferromagnetic metal consists of atoms that have an incomplete inner core of electrons and a crystal structure that results in high density of electron states in the energy bands formed from incomplete atomic inner core. It also has an atomic spacing that allows for exchange effects among electrons in the energy bands associated with the incomplete inner core level. If the atoms in the metal crystal are too widely spaced, the exchange effects are too small to cause alignment of the magnetic moments of neighboring atoms, and the crystal will not exhibit ferromagnetism. The requirement of high density of states stems from the Pauli exclusion principle. This principle prohibits electrons with the same spin from occupying the same energy level. Consequently, if the density of electrons states is relatively small, electrons will need to occupy higher energy states in order for all to have the same spin. If the increase in energy resulting from the occupancy of higher energy levels exceeds the decrease in energy resulting from the electron exchange energy, the structure will not be ferromagnetic. Anyway, you don't need to worry so much about the last paragraph here, but the paragraph regarding the nature of, for instance, a type 304 alloy pre and post a mechanical deformation and it becoming magnetic is very important, and the relationship between these two lattice structures. Secondly, the whole process of magnetization. So, yeah, I've got stream pausing as well, probably at my end. So I'm very sorry about that. It might just be because this connection is contended on this particular day. So, yeah, okay. Anyway, the replay should be fine. Okay, so that is the key points. Now, what I said earlier is that the ball is stainless steel, the outer ball, and the outer cylinder is stainless steel. That's what you see evidence for in the video. But I believe that the inner cylinder, which is actually appears to be a little thicker, is actually ferromagnetic material. And why is that important? Well, it's because of difference in thermal expansion coefficients. And how does that actually play out in the real world? Well, I did my maths and I'm trying to find it here. Somewhere. Oh dear. I did a calculation, and it is not inconsiderable when you consider that the thunderstorm generator can be, you know, best part of a meter long or 80 centimeters or something. So on the basis that it was a meter long, let's say the central ferritic steel rod. I did a calculation, and the calculation, I will put the references in the blog later. But essentially, if you have, and I chose 316 stainless, not 304, but if you take 316 stainless as the stainless outer sphere and the stainless larger cylinder, compared to a mild steel in the center, the stainless steel would grow effectively 8 millimeters longer over a temperature of 800 degrees over the same length of mild steel. That is about 426, 427 Celsius, and that is within the ballpark of the temperatures that have been observed coming out of the hot end of the thunderstorm generator. So, with those two things in play, and from my quick look-see of the section that was so-called imploded, then it would account for that displacement, because the ferritic steel, the mild steel, is not expanding by as much as 8 millimeters. The stainless steel sections are expanding 8 millimeters more than the mild steel in the center, and it's just high plastic deformation. It's an incredible amount of pressure, because the atoms are going to be doing what they want to do, and they're not going to really pay attention to whether you think that the stainless steel ball is strong or not. So it is not about gas pressure, in my view. It is not about some magic magnetic moment that's going on that's causing that particular so-called implosion. It's the difference, in my view, between the ferromagnetic steel and the stainless steel's coefficient of thermal expansion. And let me just pull up that video again, because it's pretty much in line with what you see. If we go where that particular bit is, and we can try and get it in shot. I don't know if you can see, but up here, the movement that has gone, is that around about 8 centimeters? I don't know, but certainly it's moved in exactly the place that I would expect it to, with the difference in thermal expansion coefficient. And so what this has in terms of implications here is that you would want all of the metals that it is comprised of to be the same metal. That is to say, if you could make this whole thing, for instance, as a 3D printed Inconel part, if it turned out that Inconel was suitable, then that would be advisable. At the very least, you would want it all to be made of exactly the same metal. So that is one thing looking forward that has to be done. Of course, when Malcolm was making this original unit, he's getting whatever stainless steel. I mean, this is stainless steel tube here, but this is definitely a mild steel pipe fitting, right? And this material coming out the end here is ferromagnetic mild steel. So you've got a brass fitting there, mild steel here, mild steel here, stainless steel here. So it's a whole mishmash of stuff, but it's what you would expect when you're prototyping. And again, here, this is mild steel with the bit that's attached to the actual engine for the coupling there. And then this goes into the stainless steel, and this is stainless steel. But unfortunately, it would appear that it has this mild steel in there. But it might not. It might be another stainless steel, but it's not got the same thermal expansion coefficient. Okay. Yeah, so Hui has said, so if the same material is used, then the expansion differential should go away. Absolutely, you had understood my point here. Okay. The materials were fairly irrelevant for majority of the performance. I think the most important aspect that is driving this is maximizing the water vapor in the air coming into the system, and the fact that it flashes to water, steam, dry steam, instantaneously. And I believe that that does exactly what was going on in the Armstrong static generator. And you're getting extreme charge separation in that flashing, that instantaneous flashing as it's going from one state to another. And as it goes into a vortex, you get further charge separation and extreme shear. And this leads to the turbulence that's required to create the electromagnetic structures that are required to do the work. So that is that part of what I wanted to say. And the next video, which I think I do have access to directly, which is better. Yeah. So using sensors. Okay. So this one here, I'm using my trusty old Samsung S7, which you can pick up now for about $60 or $70, and they're brilliant devices. They have a no AI on the 12 megapixel camera at the back, so you just get your what's actually happening, what rather than what some artificial intelligence thinks the picture should be. And so you'll see some microscopy that I will share in the coming days that were taken with this and the Narugo lens at 400 times, which revealed some rather beautiful things in addition to what we've already shared. But I'm using this free tool called Sensors Multi-Tool, and so for replicators I would suggest that you do not take a magnet to your device until you have kind of done a rough profile of what's going on magnetically, because as I said, if you have any variation in thermal expansion coefficient with stainless steels, you could end up by finding that you have some ferromagnetic areas being created, and that if you then run a magnet over them, you will actually magnetize those areas, and that may even affect the way the device performs. So yeah, it's very important to establish what the magnetic nature is before you go ahead, and then before you ever get a magnet near it again, you want to see what magnetization has occurred. And this is where it gets a little bit interesting, which I'll talk about in a little while. Okay, so here we go. This is the bit that's so-called imploded, and I am saying that this is a thick piece of ferromagnetic steel. This is stainless steel, and because this moved, partly because of the weld, but mostly because of the difference in thermal expansion coefficients, that so-called imploded. And you can see there is some so-called magnetic field adjustment there. Now, it isn't that this is magnetic, it's ferromagnetic, and that it may have been magnetized. It may have been magnetized by application and repeated application and demonstration with a magnet, or it might have been magnetized, and here is the important point here. It might have been magnetized by the charge flow in the thunderstorm generator. And because this was demonstrated with many times with a magnet, I don't know whether it was the magnet that caused the charging or whether it was the thunderstorm generator. So it is interesting that it's magnetized, but we can't nail exactly why that is. And then if you go back and we look at the actual, what I do is I rotate here, and what's interesting about this is I rotate it it does go up and down, but again, that might just be the amount of time someone's rubbed a magnet over this and magnetized the ferromagnetic domains. As I'm going along the steel rod here, yes, we have a very strong change as we go into the crack here. But as I saw prior to doing this test, Johanna James had placed the magnet a number of times into the corner there, and I don't know how many times that had been done before. So the magnetization could have been done by demonstrating that it seems to allow a magnet to stick to it, if you know what I mean. And that's just potentially because it's ferromagnetic. And again, across the weld point, we have this, and this could be a combination of the thermal expansion and physical deformation of the stainless steel by the actual welding process. Or it could be that this is ferromagnetic for whatever reason, because of the type of weld, and then with the thunderstorm generator charge separation going on there, it then further magnetized it. So all of these things are, you know, they're not for me that amazing, but they are points that replicators need to explore. Now, in this part of the video, I rotate the ball, and it appears to have a sort of a flattening off, and it goes down and it goes down more, and so on as you go round. Now, when you think about this, there might be an obvious reason for this, and that is that the swirl guide, the bit that attaches to the output from the electrical generator, is actually ferromagnetic, and as I rotate that around, that is influencing the magnetic field on there. Okay, and you would expect that to do it a number of times as you rotate it around 180 degrees. So I don't think there's anything particularly special going on. It's pretty explainable. But where the interesting things comes is for replicators is define if there's any magnetization before you do anything to it. Particularly do not get a magnet near it. Because what you will have to do is, to remove that magnetism, is you will have to do two things. One, you will have to raise it to 600 to 750 degrees C, let's say, something around that ballpark, to go through the Curie point of the stainless steel to mess up those magnetic domains. And then you will have to anneal it, and you will have to anneal it with additional nitrogen to get in there and stretch out and switch the nature of the crystal structure from the BCC to the FCC. By adding nitrogen in there. And this is what George Lush is doing by doing this annealing process. And so really don't get a magnet near it. Use the sensors multi-tool that you can see here. Free application for Android to get a sense of what's going on, and then see what happens over time. Because what I'm going to show you in this next part of the video, this analysis here, could be the key, or potentially is one of the main ways in which the thunderstorm generator is actually doing its work. Now, if you look through the first video, Malcolm says that he took that 8-year-old device and he put it on the generator that's in the workshop there, and it seemed to do some of the remediation, the sort of lowering of carbon monoxide and carbon an increase in oxygen, without anything other than just the thunderstorm generator on there. The implication is that there's something embedded into parts of that metallic work that is potentially playing a role. Now, we do know that charge clusters, exotic vacuum objects, can live in metals indefinitely. That is being said by Ken Shoulders, and certainly it would appear that that is the case when looking at, for instance, the 2007 aluminium coral twist sample from the MFMP, which we acquired from John Hutchison, and other people in the Lion reactors and in the work of Zatelepin and Baranov and so forth. They have seen these structures exist for a long period of time. So why would they be there? Well, if you have the sort of Armstrong level of electrostatics being generated by that flashing of steam, and you have this incredible vortical nature with literally plasma in there as well from the explosion in the internal combustion engine. And that's going around this vortical thing. Now, I've discussed this with Malcolm. Of course, if you just had a tube and you're adding water vapor in there, I would expect it to probably work reasonably well or similar, at least in some of the effects. And one of the replicators, at least I know, is going to be exploring that. However, what you do have with a sphere is you have a larger surface area in which to transfer heat and potentially transfer charge, and possibly even, if they're neutral, charge clusters into various parts of the system. And then also you have another thing. The two objects that have the minimum surface curvature are the sphere and the torus. Okay, and that is why we have those kind of things in, for instance, Tesla experiments. You have a sphere or a torus, or you know, a pill shape, that is a cylinder with a spherical, hemispherical cap on either end. Those are the options, sort of like the tic-tac so-called UFO. Those are the options, and I've discussed that before, because you have this minimum surface curvature. But there is this not minimum surface as you go from, you know, on a pill, you've got the cylinder section going into the hemispherical section. So really, it's the torus and the sphere. So that means that if you are going to want to optimize a self-organized structure over a surface, then the sphere is probably the thing to do it. Now, what did we see when we went into the center of this device? Well, it was very interesting and unexpected by Malcolm. And we are going to see, I think, something that really, if it is what's going on, you know, when I saw that video of the things kind of coming out and going in, I expected monopoles to be inside that cylinder, not able to go through, but able to project through their flux loop. Okay, and moving around along with the overall kind of space charge arrangement within the thunderstorm generator. So that's what got me excited. So I kind of imagine what I would see on the inside. Now, we're going to share videos of the outer spheres inside later, but the inner spheres outside had very interesting features on it, and they were these pock marks, and we variably called them leopard prints and so on. But these looked very, very interesting to me indeed. And even at this scale, it was quite exciting. And as you go in, and we looked at these in greater magnification, they became even more exciting to me. So this is not exciting to me. This is, in my view, just where the steel has been abraded to polish off a weld or whatever. But as we go in, this looks to me, this area where Malcolm has rubbed off this coating on the surface, this looks like maybe even crystals in the metal forming, or something that's deposited on the surface has formed some sort of crystal domains in there. So that might be what's going on there. But as we go through this video, and I recommend you have a look through it, there's a lot to be seen. In this area, it's different, but again, you get these impacts. So, and these deep pitted impacts here, very deep pitted impacts. So, and these deep pitted impacts have a lump in the center and a ring around the outside. Lump in the center, ring around. In fact, I've got my face in the way. So it's not very clear, but this is in 4K, and I will pick these out, these particular features, and put them on the MFM, on the remote view blog later. So this whole group up here looks very interesting to me, and not only the black spots, but the larger ones here. And I would like to, for instance, take a section of this and put it under the large format SEM ideally. As we go through the weld point here, we go through this to this new area down here where these pockmarks, these leopard prints, these looked extremely familiar to me, and I'm going to show you why in a minute. Particularly at this kind of magnification, very, very familiar indeed. I don't think it's arcing, Cookie Couture. I think it is involving charge clusters, exotic vacuum objects, but I don't think. I mean, when these things blow up, they release a lot of electrons. So anyway, there's a lot to go through here, and we looked at various different angles and stuff. Unfortunately, we didn't have a tripod, which is a great shame, because I would have been able to do a shift focus and created very, very high quality macro images. But I think we can understand enough from what we did get. So these are very, very interesting. So what I've done is I've taken a couple of screen grabs. So here you can get an idea as it goes across here. That there is some depth to these things, and there tends to be something in the center of them as well. Okay, so take your time to have a look at this video and step by that using the dot and the comma on your keyboard. You can step through on YouTube one frame at a time and so forth. But I've got some images that I composited up by taking screen grabs of particular frames, and I will show you those now. So in this particular one, what we noticed is that you can see this is a slightly hexagonal type mark here, potentially. And in the center, we have one of these little crystals. You can see how big it is because we got the lighting from the side, and you've got a long shadow here. Long shadow, long shadow. Okay? There's dark patches. Now, unfortunately, because the camera is shaking around, some of these lines could be just from motion blur. So you have to... that needs further improvement in getting the visuals there. Now I have this other image which I think really tells the story of what I want to share with you now, and that I'm going to see if anyone can see where I'm going with this. This is a couple of frames, and I've just you know, taken the collective from them, but what you're seeing is dark area, white area, and then this sort of other type of area in between. And there's kind of what look like clusters. Are they clusters? I don't know. There's definitely ones overlaid. Look on this, up on this corner here. There's one there, and then this is overlaid, and this is overlaid. Okay. Ken Shoulders Pearls, Hui says. It does appear that there is some feature in many of the center of these. It tends to be this white spot, whatever it is. It's a little bit more obvious in some of the other images, like the title frame that I... What did I do then? Yeah. Okay. So they're not the best ones. It's not ideal, but we did make some great advancements in my view, particularly with this shot, and I'm going to show you why. And see if anyone will guess where I'm going to go with this. So Ken Pratt said, these look similar to my Evo, and I've got something over the video, Rocks videos, okay, yeah. Okay. I'm going to ask you to get out those that have bought the book on Amazon for cost. Matsumoto's Steps to the Discovery of Electronuclear Collapse, Collected Papers 1989 to 1999. And I want you to look at the Fusion Technology, Volume 24, November 1993. So exactly 30 years ago this was published. And it's Experiments of One-Point Cold Fusion, which was submitted on October the 20th, 1992. So this particular paper spent a year, just over a year in peer review before it was published. And I specifically want to refer you to page 178. Okay, now I'm going to get that up for those people who do not have the book, so that you can see what I'm blathering on about. So let me get that for you. Okay. So I'm looking for page 179. Not that page. So this is the paper, Experiments of One-Point Cold Fusion. And experiments of one-point cold fusion have been performed by electrical discharging in ordinary and heavy water mixed with 0.6 molar of potassium carbonate. A platinum pin anode was located perpendicular to a copper plate cathode. After discharge, the surfaces of the copper plates were examined by optical microscope. So, it's a solution in water. Therefore, if you've got a discharge in water, you will create charge separation and you will create oxyhydrogen gas, whether you like it or not. This is an HHO system, and that is, I believe, what is going on to a degree in Malcolm Bendel's device. After discharge, the surfaces of the copper plates were examined by an optical microscope. Many ring spots caused by gravity decay of single and di neutrons were separately distributed on the plates. Now, this is what he thought of in 1992. But if you go to a paper in, let me get that up so that we can talk to it precisely. There is a paper, or rather a note to the editor in 2001 in Fusion Technology, where he is admitting where he ended up in terms of his thinking, which differed from where he started. Okay, so let me just get that. I've got to find it. Okay. So it's from July 21, Fusion Science and Technology, Volume 40. And it says, recently we have observed an increasing number of researchers who began to recognize an important role of small-sized charged clusters that could be generated during cold fusion-related experiments. These curious clusters were a key point to understanding the various extraordinary phenomena observed during the experiments. An excess heat production, nuclear transmutation, and ball lightning-like phenomena. New kinds of nuclear reaction could take place within the charged clusters. As Lewis describes in his letter, 3 models were proposed for the curious charge clusters so far: plasmoids by Lewis, electron beads by Shoulders et al., and itonic clusters by me. This is Matsumoto. Lewis pointed out similarity between plasmoid observed in plasma-focused discharge experiments by Nardi et al. And traces that were obtained from a nuclear emulsion during my electrolysis cold fusion experiments. These ones, right? I appreciate him for having carefully watched my data. Shoulders et al. Proposed a model of electron beads by performing a discharge experiment. I proposed a model of special clusters, the NATO model, as soon as cold fusion was published, and developed it by performing experiments of electrolysis and underwater spark discharges. Probably we discussed similar objects with different terms having different contents. According to the NATO model, a special state of clusters called itonic clusters could be effectively generated mainly on the surface of atomic clusters when many electrons were charged. Here, many electrons were assumed to be interconnected. Bonding of those electrons could be so strong that the clusters were violently compressed. Several kinds of nuclear reaction could take place within the itonic clusters. The most significant reaction was nuclear collapse, which induced an explosion and during which mesh-like networks of interconnected electrons could be broken up. My 3 ring traces of these references were products of the those simultaneous explosions. Here, I have to apologize to readers for an insufficient assignment made in reference 5, and I believe this probably is reference 5, that quad neutrons collapsed. It was made clear by later experiments that clusters that collapsed were atomic clusters that could have a diameter of hundreds of micrometers and involve much more nuclei. Very amazingly, it was also found that the ring products consisted of conventional elements, mainly carbon, not dependent on collapsed materials. This process was called nuclear regeneration. Furthermore, white wispy markings between my ring traces were remains of interconnected electrons, which were more obviously shown in Figure 3 and of reference 6. Those electrons formed networks like mesh and played an important role in causing curious phenomena like ball lightning during cold fusion-related experiments. So I would agree that Lewis's idea that the ring craters and markings, like brush discharges obtained by Nardi et al., resembled well the ring products and white wispy markings during my cold fusion experiments, respectively. But it would be much more important for science to not only observe superficial phenomena, but also to understand the physics involved there. An element analysis would easily resolve the problem. If nuclear collapse were involved in the experiment of Nardi et al., a large quantity of carbon element should have been found in the ring craters. Lastly, I would like to point out that the itonic cluster were different from plasmoids. First, the model of plasmoids could not explain the feasibility of nuclear reactions. First, the model of plasmoids could not explain the feasibility of nuclear reactions, especially nuclear collapse, because of their weak bonding force. Second, itonic clusters could be generated not only in the plasma, but also in other wide fields, for example during high-pressure compression or thermal heating. Outer orbital electrons of atoms involved in materials could be easily interconnected. I will publish many beautiful pictures elsewhere that show mesh-like structures of interconnected electrons formed in natural phenomena. Anyway, he's saying that plasmoids is insufficient. I'm minded to agree. Ken Shoulders, if he thought plasmoids were sufficient, he wouldn't have come up with new names for what he was observing. I think exotic vacuum objects, but most importantly, whatever it is, it's ball lightning. Okay? Now, when we look at this, okay, when we look at these structures here, and we look at what was observed by effectively ball lightning striking, and not just a few dineutrons or neutron collapse, as he admitted here, it was hundreds of microns across with vast numbers of nuclei. Okay, what did he see? He saw this. Again, he's saying gravity decay of dineutrons in ZOB, gravity decay of neutrons. Does this look like this? Maybe. Possibly. Possibly. Got a lot of similar things going on. What about this? Does this look similar? What about these, my friends? Does that look similar? Is that something like what that is? Is it? Is it? I think it probably is. I mean, look at this structure here, right? Look at that structure there. Now look at this structure. And this there's millions and millions of these on the inside. Okay? Now, there is an assumption by Matsumoto that these are single events. Maybe they are where a flux loop, a soliton of an exotic vacuum object has bound itself into metal that it's made ferromagnetic. It's got locked there and it is able to do work indefinitely. Or maybe the after effects of a matter collapse leaves an echo, a vacuum current structure that is bound into the inner sphere of the thunderstorm generator, and that does the work. But anyway, this is observed nuclear reactions from detonation into or high charge separation into a water, and these are the impacts on a copper plate, and these are the structures observed in the thunderstorm generator. And so my argument that you have plasma, you have flashing of maximally grams per kilogram containing water, air, and doing the Armstrong effect, which is known to create very large electric fields. The last point I want to bring to bear here is that of Anatoly Klimov. So if I can bring this up. This is the work of Anatoly Klimov. And what Anatoly Klimov has is a reactor here where he has, if I take my mugshot out, he has a Tesla coil. It's bound to here. That's why you've got this very large thing here separating the high voltage from the ground. And he has a almost like a Rankle vortex system with a vortical flow in here to keep the plasma in the center. Other people have copied this most recently. And you can see as the system works, this is with water chamber in a target. So this is doing something similar. He starts seeing, and he's calling this X-ray spectra of a heterogeneous plasmoid. As this works, he sees production of elements like, neon, interestingly, because neon is something we've observed in the work of Binzhu and Huang. Sodium, magnesium, I think aluminium, silicon, phosphorus, sulfur, and calcium. And these are the things that you normally see synthesized. And he actually did a time analysis. So at initial discharge, you've got the OH group, the argon, which is the cover gas in there, and hydrogen lines. After 15 seconds, you have got nickel, which is in the target, but you've got sodium appearing. And then after 25 seconds, you've got potassium appearing. So this is, the longer it goes, the more elements you start seeing appearing. And so, yeah, he's gone back to that. And that's an advert. Okay. So essentially, you can go and have a look at that. It's called Experimental Research on the Physics of Plasma, so forth, by Heterogeneous Plasmoids by Dr. Anatoly Klimov. And so what I'm saying is that within the reactor, it's important to have the same metals. Otherwise, you're going to get these critical failures. How you go about doing that in the most efficient way, the most predictable way may be to have the whole thing produced by direct laser metal sintering. Maybe not. And then once you have that, there could be a conditioning time. Now, how long that conditioning time is, that's to be determined. But it could be that once you've got your thunderstorm generator conditioned, and it has these embedded marks, these shadows here on the inside of the thunderstorm generator, that it is ready to go from that point onwards, and it may not even need other components to work once it's been conditioned. You may actually be able to simplify it after that point. Anyway, that all remains to be seen. And then once you are, the magnetic anomalies could just be observed by welding thermal expansions and thermal expansions between different thermal coefficients in the metals. And then if you actually have very charged stuff rotating around. Oh, so that's what I was going to mention with the inflow of Klimov. He actually can generate power because you've got a difference in charge in the center of the vortex and on the outside. So you can have two probes going different depths into that plasma channel and actually take off electricity from that. Of course, you're going to corrode the electrodes after a while, but the point being is that as you are going around the thunderstorm generator, you are going to not only get this extreme shear, you are also going to get charge separation over that distance, and that could be what's influencing what's going on in this image. Then there's one last point, is are these effectively like eddies? Because if you go to a later page in Matsumoto's book, and that is page 247, so if we go to page 247, let me get there. Those that have got that in front of them, that would be helpful. So in 247, he's talking about this very simple experiment that he conducted, exploding a lead wire into water with potassium hydroxide. And oh, that's just crashed. That's not very helpful, is it? You gotta love some Adobe products sometimes. Give me a second. Not helpful. Right, where were we? Back in the room. Steps to the discovery of electronuclear collapse. Right. And I was trying to go to page near the end. Here. Somewhere here. There we go. He describes these structures here as eddy currents. They are our sacred geometry type structures. But could these be eddy currents that are forming because of the very intense charge that's moving around? That's one other hypothesis for what may be going on. But given the water involved, the charge separation likely in the water, my first port of expectation for what is going on here is the same thing that he observed during 1 point cold fusion, which was published 30 years ago. And I'll get there in a minute. It's just above there. Honest. Yeah. There we go. So here's another one of the type of marks. And these look very similar to the marks that we see elsewhere that I want to take a sample of. He calls these electrons or itons in zone D. But these ones I think are largely equivalent to what we're seeing over here. Anyway, with that, does anyone have any questions? So the TSG should be operated with steam as an input. I think actually it may work with just water, but I think what you want is air that is maximally carrying the amount of water it can in the gas phase, because it is, above the dew point. So I think it's 27 grams or so per kilogram for something around about 33 degrees, 34 degrees. Okay. So, hey, Bob, how can I send you a sample? Well, reach out to me using the contact form on Quantum Heat, and we can arrange how to do that. So the image is from July 1997. Not sure what you're talking about there, Corky. Not entirely sure what the video that you're seeing right now is showing. I don't know. I have no idea what's going on. Is it still caching? Oh dear. I think you're seeing something. I'm going to refresh to see if it's actually showing what I'm. Terrible connection today. Okay, I meant steam from a steam engine. I think, are you referring to the Armstrong electrostatic generator? I think superheated steam. I think what's happening in the Armstrong generator is that the superheated steam is actually not being cooled by the cooling water, as someone speculated on a link that I gave, or that you can find readily on the internet. I think the superheated steam is superheating the water in that chamber, and the residual steam is going out through the exhaust. And then that water is then forced through that very difficult and tight, convoluted, shear-inducing pathway through a capillary, and then it goes from that super heated water, which has got incredible amounts of turbulence, out into 1 atmosphere, and it flashes to steam, and you get the charge coming out of the center of the soliton that gets formed with the flashing of steam. And that projects forward to the charge catcher spikes, and that accumulates the charge until you get the discharge. So Crypto Alchemist says, Bob, when are you free to come on another Real Science podcast? So, well, it has to be on a time that's fairly reasonable for me to do. Not like starting 4 o'clock in the morning for me. I'm just not going to go there. Okay. Oh, I see. Yes. It would be nice to retrofitting to a steam train. Yes, I see. We can discuss this offline, Crypto. Yes, a lot can be done. So Felix says you can do a lot to improve the photoionization. Yeah, I've suggested using the higher energy photon line of mercury. So not the 185 or whatever it is, the one that causes ionization of oxygen. You don't want to ionize the oxygen, but you do want to have, say, doped or ordinary titanium oxide on titanium. And this would produce a large number of fast electrons. And according to Matsumoto's proposal in 2000 or 2001 to the linear accelerator, you need electrons and protons. And so the other part of titanium oxide is when you get water wetted to it, it can be a photo dissociation catalyst, and the energy is also suitable for that. Parabolic mirrors, yes. Anyway, I'll talk about those aspects in another video, but not today. I have been invited to by Ashton to be his second interviewee, which will occur sometimes next week, and I will publish that. I want to talk about the lithium component and tie that into what we've said over the last 11 years, how it may be playing a role, but I don't believe it's necessary, and I want to clarify and make very easy to understand how basically everything you need to know is in my ICCF 25 presentation, both the physical experimental data and but I want to clarify why you want 3 structures rather than 2 or more than 3. Crypto is talking about how the pinkish thing. Well, you're going to see some very, very beautiful 400 times magnification of some of this of this particular sample in the coming days, and so that's going to be very fun. So for me, Corky, I don't want to get too sidetracked on this, but I have said all normal conventional ballistic devices are pointless. I've said for many years that you can knock these things out of the sky very, very quickly, and so I think it's I think this should give people pause to forget their fear of nuclear attack and so on. We just need it to be in the open, and that these things are basically neutered, as it were. A lot of people do talk about 0 point energy. I'm more of the mind of harnessing the low density mass in the universe in the form of relic neutrinos and converting that into other matter or energy and using it as a means of propulsion and energy at any point in the universe. I'm just going up to see if there's any other questions that I missed. I have no idea what you saw in terms of the stream today, but it's been telling me it's an excellent connection. Actually, you know what I'm going to do? I'm going to shut down this browser. Sometimes that fixes it and just go back in again. Huey says, what's the title of the book? It's Takahaki Matsumoto, Steps to the Discovery of Electronuclear Collapse, if that's what you're referring to. Okay, so good connection there. Okay, great. Okay, so I just want to summarize. Basically, the videos that I've shared that were captured on Wednesday. Thank you to Kyan and Johanna for manning different cameras and following instructions and capturing some nice material. I believe that most of the magnetic anomalies are due to deformation of stainless steel, application of extreme heat during welding, dissolution of chromium, damage resulting from that, and the damage resulting from the thermal expansion coefficient differences. These things can be resolved, and then it's also important to anneal these things properly in nitrogen to get them back to their face center cubic nature. I think ultimately you want to have a situation where you can create these structures. I think they are possibly either a signature of the process occurring, or they are effectively conditioning the sphere by the charge clusters such that after a while these are the things that are actually doing the work to a degree. So it might be is it cause or effect or something in between? These things are to be determined moving forward, but I think it is very interesting that these structures are extremely similar to those observed over 30 years ago by Takaaki Matsumoto and published in Fusion Technology. And nearly a decade later, he admitted that this wasn't just a few neutrons. This was actually very, very vast numbers of nuclei that are simultaneously going through the process of electronuclear collapse. So, and the key takeaway is for experimenters to not get a magnet anywhere near their thunderstorm generator, to look for any magnetism. Use the sensor's multi-tool magnetometer to see if there's anything there before and after you do experiments, and that the charge separation in the device, which will be present, and the vortex nature and the charge separation and space charge arrangement and shear processes going on, the turbulent nature of the things going on, may lead to eddy currents. And the question is, are these a result of eddy currents or charge cluster impacts or charge cluster embedding? It's quite an exciting time to be investigating this particular technology. So I think that's it from me. I'll just see if there's any other questions. It was a fairly short one tonight. Just wanted to get this out of the door to help the team developing the Thunderstorm generator and the replicators out there to potentially have some insight as to potentially what might be going on, which might be causing something more interesting than just more efficient burning of hydrocarbons. I can't do today. Crypto. So Harry says, will you be doing SEM on thunderstorm samples? Yes, I took the samples. I published a video where those samples were taken from. I've spoken to Malcolm today, and given what I've seen here in context with this, and the other areas which I highlighted during this course of this video, I would like to take several sections of that particular sphere and potentially the inner side of the outer sphere as well, and look at them with the large format SEM, because it would be interesting to see if in these spots there is a spatial arrangement of elements, and certainly, you know, many of them they have a central feature in there, like central feature here, vertical central feature here, central feature here. And are these specific elements, are these bits of diamond, are they silicon dioxide here? What is going on? So it could be that in the overall toroid, matter is being completely collapsed, but the matter that is that hits the center there might be a range of elements, or element selections of elements, and the only way to find out is to look. Don't look, don't see, as Ken Shoulders says. It's so easy to not find stuff, and you won't even know what you didn't find. Especially if you assume this is nothing interesting. If you start with the assumption that you're never going to find anything interesting because people have been doing this forever and these kind of systems and blah, 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 there's nothing special about this one, well, that may ultimately turn out to be true. It may be no better than these other previous systems, but no one has been able to have an opportunity like I did this week to go and look at one of these systems that have been running over the course of 8 years, where the inventor says, okay, you do exactly what you want and I'm not going to stop you. And that was really, really refreshing. If nothing else, Malcolm is example for someone that is willing to have his system tested. I've experienced, had very, very varied experiences with different researchers over the years, and this, I have to say, is one of the more easy to move forward with. Okay, so I'm going to say thank you very much, guys. Good night. This was THOR, magnetic anomalies. I think we've explained all of these large macro physical anomalies. I think these may be important to resolve, and it's just a manufacturing solution that needs to be developed. But for me, the huge win of this week's work was to see these features, and it just gives testament to the absolute genius of Matsumoto and his willingness to show what he saw. It's an absolutely unique body of work, well before his time, and it was a deep honor to have met him and shared the inadvertent replications we did of his work before discovering his work, so that he could pass on, knowing that his life greatest achievement, in my point of view, was not in vain. So with that, I will say thank you. Buenas noches, dobranoc, good night, buenas era. See you in the next video.